In this video, we're going to take a look at another way that we can graph absolute value functions. So to do this method, what we're going to do is start with just your basic plain absolute value graph, just that standard V-shaped graph that we know well. And then we're going to use what we know about translations and reflections and stretch and compression to move this guy around to another portion of the plane, or maybe you're reflecting him upside down or stretch or compress if other things are done to this absolute value function. So just a crash course reminder, you'll remember that if you have a function and a number is added or subtracted to the outside of the function, like +4, this is what's called a vertical shift. That's going to move the graph up or down if the number is added to the outside of the function. All right, on the other hand, if you have a number that's added or subtracted to the inside of the function, like in this case inside the absolute values, that's going to create a horizontal translation, so it'll move left or right. And then if you remember, the horizontal translations were the tricky ones because they were actually backwards from what you would guess. So in this case, if it was x minus 5, the horizontal shift would actually be to the right 5 units because it's a minus. All right. Reflections are when you have negatives, such as on the outside of the function or the outside of the absolute value. That's going to take all your positive y values and make them negative. So it's going to be a reflection over the x-axis. And then lastly, we also have stretch and compression. So instead of absolute value of x, if it was like 3 absolute value of x, basically that's going to narrow or stretch the normal absolute value graph to be a little bit steeper. If this coefficient right here was less than 1, like a half or a third or a fourth, it would actually widen that absolute value graph. So I know I went through this kind of quickly. I'm assuming you are already familiar with translations and reflections and things of that nature. All right, so let's look at an example. Let me cover that up. All right, so here's a quick example. We want to graph the absolute value of x minus 5, quantity, and then +2. All right, so what we can do is we can start with just our generic plain absolute value graph, which I'll try to do kind of lightly. This is actually not actually part of the graph, but I'll just go ahead and lightly put it in there anyways. All right, and then let me think about what's going to happen based off of these numbers that are coming here. Okay, that -5 is on the inside, so that's going to be a horizontal shift of 5 units to the right because it's a minus, and there will be a vertical shift of +2 because of the +2 that's on the outside of the function. So we're going to move this standard V-shaped graph right 5 units and up 2 units. So we'll go right 1, 2, 3, 4, 5 units, and then up vertically shifted 2 units, up 1, 2. So here was your old vertex, here's your new vertex, right 5, up 2. Then you graph that same V-shaped graph again, and you're done, right? So basically you're starting with a parent function and then using translations, reflections, stretch and compressions to graph your new function. Now, in the last video, we did a totally different method of graphing using by finding the vertex and then doing an XY table. It's very different than this. So what method should you use? Really, it just kind of depends on what method your instructor's been doing in class. If they have a preference one way or another, probably need to do it that way on the homework and on the test. If they don't have a preference, just pick your favorite. If the table method worked better for you and that made more sense, do it that way. Or if this way made more sense, where you're just translating a parent function, then you can do it that way as well.